All right, yeah, so thanks for staying until the end of the session. We have one very nice result coming up and hopefully also a nice talk. I'm pretty sure it will be nice. So please, Rad.
Thank you so much, Paul. And thanks everyone for attending this session. It feels really good to see people in person after almost 2 years. So today I'm going to talk about our paper on descending price auctions with bounded number of prices and its connection to batch profit inequality. This is not the perfect title for any paper. I recommend everyone to pick shorter titles for their paper. This is joint work with Saeed, Alaei, who is at Google Research Mountain View, Makhdoumi, who is at Duke Fuqua, and Azarakhsh, Malekian, who is at Rad School of Management. This is not a joint work with my advisor, who is sitting in the audience, Bobby Kleinberg. Unfortunately. All right, so this paper, the story behind the paper is really about an auction designer who is trying to consider some practical considerations into account. And to just name a few, for example, imagine as an auctioneer, I care about the transparency of my auction rule, or how interpretable is the payment rule to the audience that attend the auction. Or, for example, I might care about the credibility of my auction rule, and whether it can be easily policed by the attendees of the auction, or maybe third parties that are inspecting the auction rule. Or I might care about privacy of the valuations of the buyers, because in many applications, buyers care about their private types and how much information they have to reveal during the course of the auction. And finally, as an auctioneer, because of, let's say, computation and communication limitations, I might care about using these resources in a smart fashion. And then when you think about different auction formats out there, and this list, almost all of them are going to be checked by one of our favorite auctions these days, pay as bid or first price rule. It almost checks everything in this list. So let me actually explain them a little bit more. So first price auction has a very nice implementation using using descending prices, which is a kind of auction that starts with a clock that is at infinity, goes down to different levels, and determines the bidder along the way. And in this implementation, there is no need for a private communication between the seller and the buyer. So no such private channel is needed. And then with that implementation, the auction is going to have the automatic self-policing property. So if you attend a first price rule, the auctioneer should charge you with the bid that you have. It cannot be a higher or lower number. Otherwise, you will identify that the auctioneer is lying to you. And finally, it doesn't reveal that much about the buyers. Only the winner's value in some sense will be revealed to the auctioneer. So however, even though it has almost all the properties, I want to raise this question: what about the practicality of the descending price implementation? How practical is that? In particular, how many interaction rounds or communication between the seller and buyer is really needed for having a decent descending price auction? And in order to answer this question, I'm going to actually focus on arguably the simplest setting that you can think about in Bayesian mechanism design, which is a single seller selling a single item to n buyers. I assume that the buyers have independent prior valuations. They are symmetric homogeneous, which means that all the values are drawn from the same common prior distribution F. And the objective of the seller is to maximize the expected social welfare. You can think about the revenue as well, but for the simplicity of this talk, I'm going to focus on the social welfare. And I'm going to mainly focus on the regime when the number of buyers is large for some technical reasons. As I said, you can think about revenue, but I'm not going to focus on that. I'm going to mostly focus on welfare. And finally, in the paper, we study generalizations when you have multiple units of the same item. But for the sake of this talk, I'm going to stick to m equal to 1 case. And then we are thinking about designing a mechanism that maximizes expected social welfare at the induced Bayes-Nash equilibrium of the game of incomplete information that will be induced by a mechanism. And now you think about different mechanisms you can think about in this space. And as you increase the competition among the buyers, how much improvement you will have in the performance. So on one side of the spectrum, we have a mechanism. Nick called it a static threshold. David called it single posted price. Marcus called it uniform threshold. And I'm going to call it anonymous pricing to just give you another name. So it is the case when you have no competition. So the seller is posting a single price. And among the buyers who are willing to take that price, you're going to pick one of them uniformly at random and charge the person with that price. And now suppose I give you the permission to induce more competition, then all the way you get to auctions. So anonymous pricing is nice. You can essentially extract 1 minus 1 over fraction of the optimal welfare by a single price, thanks to work of Chichi-Yan back in 2010, another work by Jose Correa and co-authors in 2017, and some other follow-up work. And then if you are allowed to induce competition, then the second price auction or first price auction essentially is going to be VCG, is going to maximize social welfare. So this is really nice, and competition is really helpful. Not surprising, competition is going to make the market efficient, but it comes at a cost. And in order to see the cost of competition, and kind of related to the question I started the talk with, which is about the implementation of the descending price auction, I'm going to introduce a fairly general class of pay-as-bid rules that are going to interpolate between anonymous pricing and first price auction. So what is this class? Think about a descending price auction when the auctioneer is limited to a particular set of prices. So this set can be finite or infinite. It can be countable or uncountable. And when I say KDPA, DPA is an acronym for descending price auction. What I really mean is an auctioneer that commits to a sequence of K prices, P1 to Pk. P1 is the highest price, Pk is the lowest price. And think of now a clock auction. It starts at the infinity. Clock is going to be infinity. And it only takes values P1, then P2, then P3, all the way to Pk. And at each clock, the auctioneer is going to ask a binary question from the buyers whether you want to buy or not. So at some point, there will be some buyers that they're willing to take that price. At that point, the auction is going to terminate. Among the people who are willing to take the price, the auctioneer is going to pick one uniformly at random and charge that person with the price. To just give you a demonstration, so you should think of the following. I commit to the set of prices. Now it defines a game of incomplete information. Each buyer, given her valuation, is going to decide at a threshold BI of B, the bid of that buyer essentially, which is the point that after which the buyer is going to attend the auction. So the price is now at infinity. So we have 4 buyers. These are the thresholds for starting to attend the auction. At price P1, no one is willing to attend the auction, so I'm going to continue. At P2, there will be 2 buyers, 2 and 3, who are willing to stay in the auction. Now they are the candidate winners. One of them is going to be picked as the winner. And now the auction is terminated, and I have a winner. All right? So it's a fairly simple and general auction format.
We pick the winner uniformly at random.
Yes, and it is actually essential in our result. All right, so now let's actually look back at the previous slide. So anonymous pricing is, in fact, a 1 DPA auction when the single price is equal to the anonymous price. And then if you look at the first price auction, it's an infinite DPA auction when the prices can take any real values between 0 and infinity. All right? And now you can start seeing that as you are given more number of prices, your performance starts increasing. Basically, as you have more communication rounds, with 1 round of communication, you can extract 1 minus 1 over fraction of the optimal welfare. And then with infinite rounds of communication, you can extract optimal welfare. So then the natural question, which is related to the practical implementation of descending price auction, is what would happen if I give you a limited number of prices? So in order to formalize this question, let me define this notion, which I'm going to call it welfare competitive ratio. So it is basically the expected welfare of a descending price auction with a set of prices divided by expected maximum welfare when you look at the worst case across different distributions. So for k equal to 1, this welfare competitive ratio is equal to 1 minus 1 over E for a particular anonymous pricing. For k equal to infinity, essentially, you are going to get 1 competitive. And the research question I'm asking in this paper and in this talk is basically what would happen in the middle ground regime when you have k number of prices. How fast the welfare competitive ratio is going to converge to 1. So you know that at k equal to 1 is equal to 1 minus 1 over E, and it's going to converge to 1. So the question is how fast you will have the convergence to 1. And this is why I said the title of the paper is really bad. So I want to call the paper a few prices more in the next iteration. So the main result is that with a few prices more, you can actually extract more welfare, drastically more welfare. In particular, given any distribution F, there exists a sequence of k prices such that they obtain a competitive ratio of 1 minus 1 over e to the power k up to a small lower order terms of n. So basically little o1 as a function of n is in the competitive ratio. So if n goes to infinity, essentially you can obtain a competitive ratio of 1 minus 1 over e to the power k. So you have exponential convergence to 1. For example, if k equal to 3, with only 3 prices, you can extract 95% of optimal welfare. And the same result applies to revenue by the standard trick of payment equivalence when to replace virtual values with the values. Any questions about the result or the setting? Yes, Matt?
Is this tight?
We don't have any tightness results. It's a very great question.
And second question, you stated this specifically for Bayes-Nash equilibria, but descending price auction.
Correct.
Are the results sensitive to that, or you expect the same thing would hold if you did a descending price auction?
It's very sensitive to that. So basically, I have a negative result for example, ascending price auction in the Bayes-Nash equilibrium. But these are really great questions. Yes?
Is that little one term, is there like a closed form for it that is omitted for complexity reasons that you guys derive?
So there are certain classes of distributions for which you don't need that lower order term. For general distributions, you actually need that. It's for technical purposes in some sense, if I answered the question.
If it's not what it looks like.
What does it look like?
Or is it we just prove that there exists some little one term?
No, so we have an explicit characterization of that term in the lower bound results, but I don't remember actually the functional form. It's 1 over a square root n, I believe, but I might be wrong. Yes, please.
Related to that, can you provide a bit of intuition on why descending price auctions perform worse when there's like a small number of buyers?
Great question. So let's take that offline. Yeah, it's very technical. I don't think it's actually that much intuitive, but that's a great question. All right. They depend on the distribution, but they're quantiles, they don't depend on the distribution, as you will see soon. All right? So in the rest of the talk, I'm going to basically start with the Bayes-Nash equilibrium characterization of this game of incomplete information. And from that characterization, I'm going to show you how you can reduce the problem to a new variant of profit inequality, which I'm going to call it batch profit inequality. And then if time allows, I'm going to touch the surface a little bit, show you how you can essentially obtain a profit inequality for the batch profit inequality setting using extension of the concept of balanced prices. All right, so let's start from the easier one. So when the auctioneer commits to a sequence of prices, you have a game of incomplete information. It's actually a fairly symmetric game. And you should expect that there is a symmetric Bayes-Nash equilibrium. But one question is, does the game have any other B and E? And in fact, thanks to a beautiful paper by Shuchi, I think she was in the audience, and Jason back in 2013, there is a class of symmetric auctions called rank-based auctions, and they only have a unique pure B and E. And this auction is actually landing in that class. And because of that reason, you can essentially show that there is a unique pure Bayes-Nash equilibrium for this game. And that's actually the unique equilibrium, unique B and E for this particular game. Now, assuming that such an equilibrium is the object of interest, then essentially for each buyer, you have a bid function, which is going to be a step function. So this step function only takes values p1 to pk, has a step at locations tau1 to tau k. So essentially, if the value of the buyer is a number between tau I and tau I plus 1, the buyer is going to bid pi plus 1. And all the buyers are going to use the same step function as their equilibrium behavior. All right, now thinking about this equilibrium behavior of the buyers, we can relate the sequence of thresholds to the sequence of prices. In fact, there is an almost one-to-one mapping between them. So what does that mean? So given any sequence of decreasing prices, there is a sequence of decreasing thresholds for the, I call them B&E thresholds, sequence of B&E thresholds that are induced by those prices. And given any decreasing sequence of B&E thresholds, I can give you a sequence of prices that induce those thresholds as the Bayes-Nash equilibrium. So because of this characterization, which is actually not that hard, and also is the kind of closed form characterization, when you're optimizing over prices, you can change your decision variables to B&E thresholds. And now imagine that I'm optimizing over B&E thresholds. The question is, given the, how can I design those thresholds in order to obtain the type of approximation of the welfare that I'm interested in? So thinking about the problem of designing the thresholds, let me introduce what I call the batch profit inequality problem. So this game has k rounds. Remember that k was the number of prices or number of thresholds that we are interested in. In each round, I have a threshold. In round 1, I have threshold tau 1, round 2, tau 2, all the way to tau k. At the beginning of each round, I'm going to look at all the buyers and ask them whether any of them has a value that passes the threshold. If all the buyers' values doesn't clear the threshold, basically all the values is smaller than tau I, then the game goes to the next round. So for example, in this animation, all the values are smaller than tau 1, so the game goes to round 2. Now, again, all the values are smaller than tau 2, games go to tau 3. Until I get to a point that there exists a buyer whose value clears the threshold. So at that point, among the buyers whose value passes the threshold, I'm going to pick one of them as the winner. So note that here I'm not considering any equilibrium behavior. Basically, I'm thinking about a pool of myopic buyers that behave exactly as I mentioned. All right? So the goal of this problem is to design the thresholds to essentially maximize the expected value of the winner. And in particular, I'm trying to obtain a comparative ratio against the profit benchmark, which is the expected maximum value by designing the thresholds. So how is it related to the descending price auction? So here is how it is related. So find a set of thresholds that obtain a profit inequality result for this problem. Then if you look at the set of prices corresponding to these thresholds, then the same comparative ratio will carry over to that price. And see, it's because of a very simple observation how this problem is actually constructed. So the winner of the KDPA with set of prices that induce the thresholds tau 1 to tau k as B and E is going to be the same as the winner of the batch profit problem with thresholds tau 1 to tau k. Okay? So the remaining question is how can we actually design the thresholds to obtain social welfare approximations for the batch profit inequality problem. So I'm just going to explain the high-level idea. So thinking about the one-round problem, this is just the anonymous pricing problem. So when you think about the anonymous pricing, there is a trade-off between the probability that there exists a person who is going to pass the threshold and the probability that if you pass the threshold, you're going to be among the winners given the tie-breaking rule. So as I increase the threshold, then the probability that there will be at least one person who passes the threshold is going to go down. At the same time, if you pass the threshold, the probability that you will be among the winners is going to go up. And the concept of balanced prices is setting the threshold so that these two probabilities are equal to each other. For the symmetric setting, you basically pick a threshold so that both of these probabilities are exactly equal to 1 over e to the power 1 over n, and that gives you the 1 minus 1 over e result. Now, we think about 2 rounds, which is when you are allowed to have 2 thresholds, tau 1 and tau 2. Then you can start writing down basically the contribution of the first round, which is exactly as in the previous slide, plus the probability that you go to the second round times the expected contribution from the second round. So in the second round, you're going to deal with the conditional distribution. But the type of expected welfare you get, the form, the algebraic form, is exactly the same as the expression you have in the first round. So now you can start thinking about recursive balanced prices. Basically, a set of balanced prices such that the probability that there exists a buyer that passes the threshold is high. The probability that if you are a winner, if you pass the threshold, you will be a winner is still high. At the same time, the probability that you go to second round is high enough. So once you keep all these 3 quantities high enough, and also you guarantee that the balancedness goes to the future rounds, then you can start recursively analyzing the competitive ratio of your thresholding problem. So in particular, imagine that I kind of like pick a threshold such that in the first round, I get 1 minus 1 over e fraction of the optimal welfare. And then with probability 1 over e, I go to the second round. And then because of the recursive balanced prices I'm picking in some way, in the second round, I also obtain the 1 minus 1 over e fraction of the optimal welfare. Then this gives you 1 minus 1 over e squared fraction of the optimal welfare. And this is exactly how the recursive balanced prices in k rounds will give you 1 minus 1 over e to the power k. So here is the main result. Basically, we show that if you pick a sequence of thresholds such that the quantile corresponding to threshold j is equal to 1 over e to the power j over n, then the type of guarantee that I showed in the previous slide will happen. And by recursively arguing about contribution of all the k rounds in future, you can show the 1 minus 1 over e to the power k approximation factor. So in the interest of time, let me actually conclude my talk. So the takeaway messages is that in the descending price auction, if you're only given a few number of prices, you can approximate welfare pretty well. And the problem is highly related to this new variant of profit inequality, which I call batch profit inequality. There are a lot of open questions in this area, in particular when you think about the heterogeneous case. How would you argue about the equilibrium, and how would you argue about welfare or revenue approximations? It's a fairly difficult question simply because we don't understand the Bayes-Nash equilibrium of first price auction in the heterogeneous case. So with that, I'm going to conclude the talk. Thanks a lot for your attention.
Yeah, so we are actually a bit over time, so I would propose that in the interest of time, we take questions for Rod offline. So let's thank all the speakers in the session again and then have some coffee.